letting me know. So let's get started here on the 10th session, which is on mining social network graphs. So let me just see here if the video is set up okay. So we're going to continue here with mining social network graphs. Last time we talked briefly about this concept of locality, the local structure in a graph. And we saw how you can assess whether a graph is more likely to be a social network graph rather than just a arbitrary graph by computing the probability that if two edges exist between a vertex and two other vertices, then what is the probability that the third edge also exists between those three vertices? And this kind of local property is something that social networks satisfy more than arbitrary networks. We also learned about the definition of a clique in a graph. So a clique in a graph is a subset of vertices that are pairwise adjacent. And similarly to how we looked at maximal matchings and maximum matchings, we also talked last time about maximal cliques and maximum cliques. Okay, so that was mostly focusing on local structures and graphs. And today we're going to talk about something very interesting. And that's basically that, given a particular graph, we're going to basically determine if you have to basically break up a graph into a bunch of connected components, which edges should you remove? And what would the connected components be? So let me just fast forward a little bit here to last week's slides. Okay, we're starting clustering of social network graphs. So here's the outline for this lecture, and probably we'll finish this only next week. Okay, so the outline is the following. First, I'll briefly describe the community detection problem, which is a kind of clustering problem that you often see in machine learning and AI. Okay, and in machine learning, there are some standard methods for solving these clustering problems. There's something called k-means clustering, and there's another method called hierarchical clustering. And we'll see why there are problems with using standard clustering methods in the specific social network community detection problem. And because the standard clustering methods don't work very well, we will look at some specialized clustering methods. So to that end, we will discuss something called the betweenness of an edge in a graph. And we'll look at an algorithm called the German-Newman algorithm for basically detecting communities in a social network graph. So here's the basic community detection problem. Basically, a community is a subset of nodes such that all the people in the subset know each other very well. Okay, so nodes within a community are densely connected internally. Okay, and between the different communities, the connections are quite sparse. So you don't see as many edges between communities as you do within a community. Okay, so the community detection problem is the following. Given a social network graph, the problem is to output the substructures in the graph that are likely to be communities. So let's look at an example. If you're given this particular social network graph as your input, and you're asked to output two communities, that means that you have to output two subsets of vertices such that the vertices within each subset are very densely connected to each other, but vertices between the subsets are very sparsely connected. So probably what your algorithm should output if it took this particular graph as its input is that the first community is the three vertices A, B, and C, and the second community is the vertex subset D, E, F, and G, because you can see that there's only one edge between those two communities. So this is one community, and this is another community, and that's one good answer, probably the best one, okay? And we have to kind of maybe make the notion of a community more precise, because this is not a mathematically rigorous definition. It's kind of a vague definition, and that's part of the problem, coming up with a more mathematically rigorous definition so that you can kind of formulate a problem mathematically, so that you can assess how well you're doing. Maybe somebody else comes up with a different set of communities in the same graph. Is there some way to assess which is the better one? Okay, whose answer is better? So this is one particular answer. So I hope you're kind of getting a vague idea as to what the community detection problem is from this example that we're seeing here. Okay. Again, I haven't rigorously defined why that's the output. That's something we have to still talk about, but I hope you see what the community detection problem is. It appears that A, B, and C are very, they're friends. D, E, F, and G might be a circle of people who play table tennis with each other a lot. A, B, and C are maybe classmates in school. And then B happens to have a table tennis friend D, and so this is the network of B, a table tennis network of D. So you have different communities like that. There are reasons in the real world where, as to why you have a bunch of people forming a community. They have some commonality of interest, some common interest usually, or maybe they're in the same family or in the same class or same hobby or something. There's some reason they're all meeting together. But basically that's the goal. You know that basically, the goal is to detect the communities. All right, so